Alright, so today we're going to start off talking about igneous rocks. So there's about 5 concepts that we need to know specifically for igneous rocks. The first one is, how are igneous rocks formed? And that's due to solidification of molten rock. Now, as we already know, molten rocks are going to be classified as magma or lava. Now, magma is going to be located deep below the crust. It will always take longer to cool because it's deeper. It's not exposed to the water or exposed to the wind that would naturally make it get cooler faster. And the crystals tend to be larger in the rocks as they start to solidify. Now, if you notice, we're only really focusing on certain magma chambers. For instance, there are magma chambers that can be found here inside a volcano, and they can also be here in the upper crust. And there's also certain other locations that we're going to talk about in a moment where they can be located. Lava is when the magma comes out of a volcano or out of a vent or out of any of those areas, when it actually gets above the surface. Those are going to cool much faster because they're exposed to wind or water. And on top of that, the lava is going to have much smaller crystals that will most likely not even be visible to the eye, or at least the ones that we'll be working with here in our science are not going to be visible to the eye, or they can be completely non-crystalline, which will give it a glassy appearance. Okay, so where do igneous rocks form? Primarily, if it's lava, it's going to be volcanoes and rifts. Rifts are going to be an area where two plates are moving apart. They're diverging, which is going to allow the magma to come up and come to the surface, which we'll call it lava. Magma, like I said, will be found in chambers or deep in the earth near a convergent plate boundary. Right here I've got some examples of the pictures. If we've got a volcano, which we're going to have our lava here. Okay, here we've got our rift, which will also give us some lava. This happens to be the Mid-Atlantic Ridge. And if you take a look, it's moving apart here. And one important thing to note here is that the younger, which I'm going to denote with a Y, tends to be located right here immediately at the ridge, and it's going to slowly move away. So to make that a little bit clearer for you, just give me a sec here to delete this. Okay, because that may not have been super clear for you. We've got our younger rock here at the ridge and our older rock here towards the actual continents, because the two plates are actually moving this way. There's more than two plates right there, but primarily we're going to focus on the North American plate and the European plate. Alright, next we've got our magma chamber, which, if you notice, once again, deep below the earth, so therefore you're going to get large crystals from those rocks when they solidify, and on top of it they're going to take longer to cool. And plate boundaries, here we've got our convergent plate boundary. We've got two different plates coming together. You got your continental and your oceanic plate, and right about here they're going to start to melt, and that's going to cause either an igneous rock to form due to the molten material there solidifying, or you could also end up with partial melting, which will give you a metamorphic rock, which we'll talk about later. So crystal size, like I said before, the cooling time is really what determines the size of the crystal. If it cools fast, it could be glassy like this one, or it could be fine. And over here we have pegmatite. Pegmatite's going to have larger crystals, which you can see right here, these black crystals. I got some white crystals, because it's had a longer time to cool, because it's inside the crust. Okay, just a quick little graph showing you what's going to happen. Sorry, the scaling over here is a little bit weird, but same premise. As cooling time increases, crystal size increases, which, if you forgot, that's actually a direct relationship, because they both are increasing. Here's a quick recap of crystal size again. You're going to have large crystals if you have a long time to cool and it's going to be deep within the crust. Small crystals are going to be if it's got a short time to cool, with, once again, if it gets exposed to wind or water, and that's going to come from lava. So what is the difference between an extrusive or intrusive rock? If you look on your reference table, they actually use the words volcanic and plutonic. Volcanic meaning it comes from lava, plutonic meaning it's in the earth, like a pluton. So extrusive rocks are going to be formed near or around the surface of the crust. They're going to have small crystals, and they're going to have a short cooling time. And the way that I can always remember is that EXT reminds me of exit. And then intrusive rocks tend to form deep in the crust. They have large crystals, and they have a long cooling time. And the word right here gives it away. It's in the crust. Okay, so The last concept is what we can use to identify an igneous rock. For instance, we can use texture to identify them. So an extrusive rock is either going to be glassy or fine. In other instances, it could be vesicular. If something's intrusive, it's going to be coarse, something like granite here, or something down granite right here, which you're going to get those little dots of color there. Each of those are separate minerals. Or it could be like pegmatite, where you end up with these large crystals here, which is very coarse. In earth science, we only really deal with pegmatite for very coarse. For coarse, we've got things like granite, gabbro, and other ones that I'm going to show you guys in the rock rundown that we'll do eventually. Okay, so the middle of page 6 is crucial because this is going to give you the grouping of different characteristics. So, I want to kind of start off by talking about what a felsic rock has to offer. If you look here, a felsic rock is going to be light in color, low in density, and it's going to contain aluminum, and sometimes Si. A mafic rock is going to be high in density, it's going to be dark in color, and it's going to contain iron and magnesium, which is what lends it to having a high density, is iron's density. Alright, so the further we go this way, the darker it gets, the more dense it gets more iron and more magnesium. The further we go this way, the lighter it gets, the lower the density becomes, and the more felsic it becomes. Now if you take a look here, we've got a chart. So just a quick example. We've got our extrusives and our intrusives. Okay, so if I want to identify, let's say, granite, for instance, right here. Alright, so we're going to say for granite, it is an intrusive rock, okay, that has a grain size of 1 millimeter to 10 millimeters. It's coarse, and it's non-vesicular, meaning it does not have gas pockets. After we determine that, we're then going to go down the chart here, and we're going to stick to this side, and we're going to determine that it is light in color, low in density, felsic, containing aluminum, and then we're going to kind of take and make a bar going straight down here. And these are all the minerals that are composed inside of granite. Now if you notice, a lot of the rocks around it actually are composed of the same thing, but the characteristics, like their grain size, if they're intrusive or extrusive, are all going to determine where it lies. Now the only weird part of this chart that I've noticed is that we've got obsidian up here, which if you notice is glassy. But the weird part about it is, if you notice, it says that it usually appears black, because it does. It basically looks like black glass, but the problem with that is it's on the felsic side of the chart. And that's because if it would have had a little bit more time to cool, you would notice that it would have been felsic. But instead, the minerals that come out is the biotite mostly, and that's what gives it its black appearance along with the amphibole. So, alright, so some of the unique ways that we can identify an igneous rock. Like I said before, we've got glassy texture, and the misnomer is that a lot of students think that just because it's glassy, it can't be vesicular, which is not the case. The only reason something is vesicular is because the gas that's trapped inside of the lava or magma is then cooled with, and when the rock cools, is then traps those gas pockets. And because of that, you end up with a vesicular texture. But if it didn't have the gas, you would see that it would be glassy. Bringing us to vesicular, which is gas pockets. They are not holes. Another misconception that students have is that they are holes. It's not like we're drilling a section of the rock out. These naturally occurred during the solidification process. And then finally, we've got interlocking or intergrown crystals. When an igneous rock cools, the minerals cool at different rates, and therefore they get expressed in a different way. So the grains or the crystals are going to melt together, and then when they solidify, they're going to lock together and not be taken apart. Alrighty. So I hope this was helpful. Have a good day.